All right, guys, let's get into it. We have a review here for Chapter 8. Let's see what we can look at. Okay, this is a graph for the density of hikers per mile on a specific trail. All right, show an integral setup for the average density between mile 1 and 2. Okay, this is important, guys. The word average, right? What you want to remember for that is that average value is 1 over b minus a, the integral from a to b of your function. Okay, so for number 1, I'm going to do 1 over, it's between mile 1 and mile 5, so 1 over 5 minus 1, the integral from 1 to 5 of my function. Okay, and this is the average density, so like the average number of people on the trail, right? Okay, number 2 says use a midpoint Riemann sum with n equals 2 to approximate the average density. All right, the Riemann sum is going to help me approximate this integral right here, guys. We're still going to have this average value piece out in front of it that I don't want to forget. But for number 2, let's start with a midpoint Riemann sum with 2 rectangles. Now, my first rectangle is going to go from 1 to 3, and then my next rectangle is going to go from 3 to 5, okay? And we're doing a midpoint. So it goes like this. The base of this is 2, and then the base of that is 2. And so for rectangles, we go 2 times the height. Now, the height in this case is we're taking the midpoint. So f of 2 and f of 4, because it's the middle of those regions. Okay, so f of 2 is 35. F of, whoops, I wrote 2 right there. I meant to write 4. F of 4 is 25. So this is 70 plus 50, 120. Now that's not my answer yet because we're trying to find the average density. So I have a 1 over b minus a out in the front. So I have 1/4 of that. So the answer is 30. Okay. By midpoint sum, there's an average density of 30 hikers on the trail. I don't know, y'all. That looks pretty average to me on that graph there. Okay. Okay. For number 3, 4 trapezoids to approximate the average density. Okay. Good. Trapezoids. And I'm doing all 4 of them. So the bases here are each 1. You guys can see that though. Okay, so for trapezoids, it's the areas are 1/2 base and then 40 plus 35. And then 1/2 base and then the next one. So we did 40, 35. So then the next one's 35, 30. And then 1/2 base, and then the next one is 30, 25. And then the last one is 1/2 base, and then the last one is 25 and 30. Okay? Look, they all have 1/2, so I'm just going to add these together. So it's like 75 over 2. That one is 65 over 2. The next one is 30, 40, 55 over 2. And then 55 over 2. Sorry, gosh, good thing I caught that. That was 25 and 20. Okay. My goodness. Okay, and then that one's 45 and 2. Okay, so if I add all those up, that's 100. That is 140, so that's 240 over 2, which is 120. And again, average value is 1/4 of that. And I get 30 again. Oh, that's fun. Okay, so 30 by doing the trapezoids through there. Okay. Estimate where on the trail the density of hikers is equal to the average density. Well, check this out. I'm just going to draw through 30 on here. That's too big. There we go. All right. And say, where does that happen? That definitely looks like, for number 4, that it is at mile 3. And then number 5 asks me to write a complete sentence using numbers and units to tell what that represents. Well, when we integrate density, we get an amount. So that integral represents the amount of hikers on the trail between miles 1 and 5. Okay, so there are, the integral without the absolute value, so there are like 120, if that's what we saw what that integral was, hikers on the trail. Okay, moving right along here. Guys, we love set up but do not integrate, right? We absolutely love that. Okay, set up but do not integrate an integral, which can be used to find the, keyword here, area bounded by these graphs. All right, I always like to know what I'm looking at. Like, I really think it helps. Just a basic sketch, okay? All right, let's talk about this graph. It's a parabola that's upside down, that's up 1 unit. Okay. All right, and then let's take a look at what this is. That's a parabola. You don't really need to know the specifics. Like, we know that it's a right side up parabola. I mean, because this factors to -3 plus 1, I know it crosses at -1 and 3. So I don't know. I just know I can kind of do it like that. But it's not necessary for this problem to know exactly where that's graphed, okay? And actually, now I want to make this one a little bit better. Okay, so that's -x² plus 1. That's x² minus 2x minus 3. And the area that I am looking for is like right in here, okay? All right, so here's my setup. We're going to go top minus bottom. Now, when you look at this region, okay, the top curve is this blue one, and that's across the entire region. So that's going to be -x² plus 1. And then the bottom curve is this purple one, and that's going to be all the way across the region. And then that's x² minus 2x minus 3. Okay, now the only thing I need to do is find these endpoints. And if you're using a calculator, you can just go find the intersection points, okay? If you're using, if you're doing it without a calculator, all right, we need to set these two equal to each other and find the intersection points. Okay, I'm going to add that over, and then I'm going to subtract that over. So I get 0 is 2x² minus 2x minus 4. If I factor out a 2, it's x² minus x minus 2, which is x minus 2x plus 1. Okay, so x is 2 and -1. I'm going to kind of like make sure that that makes sense on my graph. It certainly seems to. And so then I just go ahead and go -1 to 2. And that is my setup. All right? Okay, awesome. All right, for number 7. It says, sketch the region bounded by, all right, this first one is a square root graph that is moved. If it says -2 on the inside, that's right 2. Okay. X equals is a straight up and down line at 6. And then the line y equals 0 is just the axis. Okay, and then so we're being asked to find the area of this region right here. All right, perfect. Okay, here we go. So again, we're just going to do top minus bottom. So it's the square root of x minus 2. The bottom is bounded by 0. You do not have to write -0, so that's fine, but that's essentially what we're doing. And we can kind of tell on here, just on my graph, that it goes from 2 to 6. Okay? So find the area of the region. All right, here we go. You guys, this integral is a reverse chain rule. All right, remember that a square root is like a 1/2. It's technically a u sub, but since it's just x and it would be u equals x minus 2, du is dx, I don't have to worry about any constants or anything. So I can just go ahead and integrate this. So this is going to integrate to, if I add 1 to that, x minus 2 to the 3/2, 2/3. Okay? And then I'm going to go ahead and plug that in. And I'm going to do top minus bottom. Now, when I plug in 6, I get 2/3, and then 6 minus 2 is 4 to the 3/2. And then when I plug in 2, I get 2/3 times 0 to the 3/2. Okay, if this was a FRQ, I would stop right there. I would box my answer. This being a multiple choice, or no, I mean, it's not a multiple choice. If it were a multiple choice, I'm going to show you how to do it. You do need to know how to do this, 4 to the 3/2. Well, without a calculator, the 2 means the square root of 4 to the 3rd. So the square root of 4 is 2, and then 2 to the 3rd is 8. So it's 2/3 times 8 minus 0. So that's like 16/3. Okay, and there's the area of the region. For number 8, it says, using the region from problem 7 as the base, find the volume of the solid formed by using square cross sections perpendicular. All right, what you guys want to remember about this is whenever it says the word cross section, okay, we're just integrating the area of whatever geometric shape it gives us. And in this case, it gives us a square. All right, so the square would be, that's the base, and then it would like come up like that, okay? And it's perpendicular to the x-axis. Okay, good. The base is the y value. It's just square root x minus 2. So the height of the square is also square root x minus 2. So the area of the square is square root x minus 2 squared, which is just x minus 2. This area is still going from 2 to 6. Okay? So this is a volume with these cross sections. Now, when I integrate that, x squared over 2 minus 2x. And let's go ahead and evaluate this. And let's do top minus bottom. All right. When I plug in 6, 6 squared, 36 over 2 is 18, and 6 times 2 is 12. When I plug in 2, 2 squared is 4 over 2 is 2 minus 4. Okay. So I end up getting 6 minus negative 2, which is 8. Okay, cool. And that's the area of the shape that's formed. All right. Let's move on to the next 3 questions here. Okay, set up but do not integrate integrals which could be used to find volumes of the following solids. Still problem 7. Okay, great. Remember, let me just write it down here, that it's the square root of x minus 2, and it's from 2 to 6. This is the region that we're working with. All right, so we're going to look at this area under the curve here. Okay, so now what we're going to do is we're going to do revolving. Revolving is different. You guys remember revolving is pi r squared. And right now we're going to revolve around the x-axis, which is here. Now remember that when the boundary line comes straight up to the x-axis, this is a disc, not a washer. This is a disc, and it's well, when we rotate it, there's like no hole in the middle. And so the formula is pi r squared. So we'd go pi, we usually put that on the outside, it doesn't really matter, and then radius squared. Okay? Well, the radius of this is just what the height is, which is the square root of x minus 2. All right, and that's how we would get that. Now, the next one, revolving it around the line y equals 4. Okay, that's a horizontal line that is like up here. Okay? And so we're going to have to do, this is still a dx, but this is now a disk, or a washer. I always say it wrong. That's why I should probably say like scones and donuts, right? Okay, this is going to be a donut. It's going to have a hole in the middle. So we are going to have to go big R minus little r. Okay, still 2 to 6. All right, let's see what big R is. Big R goes from the outside of this shape all the way to there. Now, when you guys look at that all the way across, it's consistent, and it's just a distance of 4. So that's big R. Now, little r is here to here. So what's that? Well, if I take 4 and I take away this, then that's what's left in that negative space. So it's 4 minus, give myself a little more room here, the square root of x minus 2. Okay? So that's how I would go ahead and set those up. All right. New figure number 10. The base of a solid is the region bounded by 1 over square root of x, 1, 4, and negative 3. Now, I think 1 over square root of x probably looks like 1 over x, but it's only it's called defined on the positive numbers because you can't take square root of a negative number. So that would be my best guess. Let's go ahead and take a look at it and just kind of see. Make sure my guess is accurate. Okay, so when I do 1 over square root x, yeah, it kind of looks like 1 over x. It's just only the positive side. Okay? Yay, look at me. All right. Again, it's just to have an idea of what it looks like here. And then it's bounded by x equals 1 and 4. So it's here to here. And y equals negative 3. That's a little weird. Okay, so the region comes all the way down to there. Right? Is that what it says? Yeah, interesting. Okay, so this is my base of my solid. All right. And solids formed by using rectangular cross sections whose base lie in the region and are perpendicular to the x-axis. So we're going this way and it'll be a dx. Heights are 3 times the base. Okay, check it out, you guys, the base. Well, from here to here is 1 over root x. From here to here is 3, because it just went from the axis down to negative 3. So the base of this like rectangle that I'm putting on here is 1 over square root of x plus 3. The height of the rectangle is 3 times that. So the height is 3 times the square root of 1 over x plus 3. Okay, perfect. So we're doing the area of a rectangle, which is base times height. So when I set up my integral, it's just literally going to be base times height. 1 over square root of x plus 3 times 3 times 1 over square root of x plus 3. I'm just going to put a square there and save myself a little bit of time. And it told me it was going from 1 to 4. Okay? And then it said to use a calculator to do that. So I can grab my calculator. 1 second. All right. It always just takes me a second to get my calculator pulled up. So here we go. Math 9 is integral. I'm going from, we said what, 1 to 4. And then it was 3 times 1 over square root of x plus 3 squared dx. Okay? 121.158 or 159 if you feel like rounding. All right. Okay, you can also do this on Desmos. You can do integrals on Desmos. So if you just go into functions and there's an integral button down here somewhere. Okay, and so you can do a different integral. So you can go integral from 1 to 4. You do have to put parentheses around it. That's one thing I noticed because I was like messing it up. And then it's 3 and then another set of parentheses. 1 over root x. Go over there. Plus 3 parenthesis squared parenthesis, and then you just have to type dx on like the computer thing, and then there we go, okay? 121.15888. So those are the two different ways that you can do it. Okay, that's it for that question. All right. This looks like a little bit of a review question because now we've got a velocity. This represents the velocity of an object moving along a vertical path, and it's only defined above -4 because less than -4 we would be taking square roots of negatives. All right. Okay, find an equation for the acceleration. Well, we know that acceleration is just the derivative of velocity. It's always just kind of nice to show what we're doing here. So if I take the derivative of this, it's -1/2. I bring the exponent down in front, right? It's a 1/2. T plus 4. The negative was already there, so I brought the 1/2 down, and it's to the -1/2. You might rather write it like this and put that back down on the bottom. So that's a decent way to do it. That's an equation for acceleration. And then an equation for the position, and it gives me a initial condition, which allows me to find C. So now I'm going to say, okay, my position is the integral of velocity, all right, which is the integral of negative square root of t plus 4 dt. Okay. Again, think of this as a 1/2. This is just a reverse chain rule. So if I add 1 to that, 1/2 plus 1 is 3/2. And then that's 2/3 plus c. And it told me to call it y of t. All right. Y of 0 is -10/3, so I'm going to find c now. So y of 0 is -2/3, 0 plus 4 to the 3/2 plus c, and that's supposed to equal -10/3. Okay. 0 plus 4 is 4. 4 to the 3/2, we already did that. Square root of 4 is 2. 2 to the 3rd is 8. So -2/3 times 8 is -16/3. If I add 16/3 to the other side, I get 6/3, which is 2 for c. So let me go ahead and write my y equation down here. It's -2/3 t plus 4 to the 3/2 plus 2. Okay, so there's my position equation. There's my acceleration equation. All right, and now it asks me to find a bunch of different things. So y is position. Okay, y of 5, so it's going to be equal to -2/3 5 plus 4 to the 3/2 plus 2. Okay, on an FRQ we would leave it like that. If we were trying to simplify this, 5 plus 4 is 9. 9 to the 3/2, we go square root of 9 is 3. 3 to the 3rd is 27. So this is 27. 3 goes into 27 9 times. -2 times 9 is -18 plus 2. So that is going to give me -16 for part C. Okay, I just kind of wrote it up there. All right, velocity at time 5. Well, shoot, velocity is just right here. The velocity is -√5 plus 4. 5 plus 4 is 9. The square root of 9 is 3, so that just equals -3. And then position at 5, that's that equation down here. All right. Nope, I did position already. Sorry, acceleration at 5. That's this equation over here. It's -1 over 2 square root 5 plus 4. 5 plus 4 is 9. Square root of 9 is 3. 2 times 3 is 6. So it's -1/6. So there are my answers for those. -16, -3, -1/6. All right. Good review question on position, velocity, and acceleration. Y'all, I forgot to do part F, dang it. Okay, part F asks me for speed. Now, guys, we know that speed is the absolute value of velocity. So at time 5, actually, let me just put it here. The absolute value of the velocity at time 5, well, from part D, the velocity at time 5 was -3, so the speed will be +3. All right, sorry, I skipped that. Okay. Cool, here's another velocity equation, another good review equation here. So let me write this out. Okay, moving along a horizontal path. Use a calculator. Excellent, love it. All right, defined, and it's going to ask me to do velocity, velocity, acceleration, displacement, and total distance. Okay, this is going to be sweet. All right, I'm going to go ahead and use my TI calculator. Okay, and I am going to put this equation in y1. To do that, I hit alpha y equals, to make it a fraction, and then it's x minus 1 over x squared plus 1. Okay, so the first thing asked me, find the velocity at 2.3. Well, this is the velocity equation. So all it's asking me to do is plug in 2.3. Okay, look, the way you do that is you go alpha trace y1 of 2.3. And I get that. That's my velocity, 0.206. Okay, let me note that. 0.206. Okay, acceleration is the derivative. I go math 8 for derivative. Put a dx right there. I'm taking the derivative of y1 when x equals 2.3. All right, there we go. Okay, so my derivative, my acceleration is 0.007835. I'll just throw a couple of extra decimals on there just in case. Okay, next, the displacement is just the integral. So it's displacement from 0 to 3. It's just the integral of this. All right. So the displacement is negative 0.0977. And then, you guys, the total distance is the exact same thing as displacement, except we do the absolute value because we know distance is always positive, right? So we go 0 to 3. We go alpha, window, absolute value, alpha, trace, y1, dx. And it'll make all the values positive, and it'll do like everything all at once. And then my total distance is 0.779. Oh, just noticing this and making sure I'm being a good student and following all the directions, okay? Show the integral setups for part C. So the displacement would be 0 to 3 of velocity. And then for part D, 0 to 3 of the absolute value of velocity. Okay? We always want to make sure that on the AP test we're showing exactly what we're doing and not just pulling numbers out of nowhere. All right, that was a totally calculated question, so I don't need that. Okay, for number 13, if a graph is concave upward, let's go ahead and just draw something that's concave upward. Does a trapezoidal approximation give a value larger or smaller than the actual value? All right, this is illustrated really well by just like drawing it, okay? Okay, here's the actual value. It's, you know, whatever this area between the curve and the axis is, okay? All right, boom, boom, boom. That's my actual value, okay? Beautiful. Now, if I do trapezoids, let me go ahead and just make like 3. Okay, 3 trapezoids, all right? I didn't make this concave up as I would have liked, but there we go. There's a trapezoid. There's a trapezoid. There's a trapezoid. Okay, can you see that the value of the trapezoids is going to go above it? In fact, whenever we have something that's concave up, I'll draw that one like a little bit more extreme. A trapezoid is going to go above, okay, the line. So when it asks, is the trapezoidal a value larger or smaller? So the trapezoidal is larger than the actual integral because it gets like a little bit of extra area on there. Okay. And then check out number 14. It goes like really well with number 13. If f double prime of x is less than 0. Now, what the heck does that mean? Well, f double prime of x less than 0. The second derivative is negative, means it's concave down. So this is just asking the same exact question, just said it in a different way, for a concave down graph. Okay? Again, let's take a look. A to B is going to be, I'm going to kind of shade this in real quick. All right, it's going to be this area from here to here. This is concave down. Now, let's do a couple of trapezoids here. All right, now I have to like super zoom in, but do you see that if it's concave down, the trapezoids are always going to be beneath the line. So if it's concave down, the trapezoidal approximation is smaller than the integral. Okay? And so we could say that this, we call the one in number 13, we call the trapezoid an overestimation, and then here we call it an underestimation, and it has to do with the fact of whether the concavity is up or down. All right. If the second derivative equals 0, what must be true about the trapezoidal value? Okay, so what the heck does second derivative equals 0 mean? It means there's no concavity. Can you guys think of something that has no concavity? Right? What would we be looking at? Something that just doesn't have concavity? I don't know, like maybe a line. All right. Okay, so just one more time here. Let's go ahead and do the area. And you guys are going to see, what happens if it has no concavity. And let me go ahead and make a couple of trapezoids. All right, we'll zoom in real big. That's that trapezoid. That's that trapezoid. That's that trapezoid. If there's no concavity, then the trapezoidal approximation actually exactly equals the integral. Okay? If there's no concavity. So, kind of cool. All right, let's see what else we got. All right, from this point on, it's kind of like a lot of review, but we'll run through these questions real quick, all right? Let's see here. Okay, list the locations of discontinuities and removable or non-removable. All right, so first, guys, let's go ahead and factor this out right here. Oh, dang, they tricked me. I for sure thought something was going to cross out, but it doesn't actually. So, -3 is a discontinuity and +2 is a discontinuity. And they are both vertical asymptotes because the top isn't 0. They're not holes. They're both vertical asymptotes, and you guys, vertical asymptotes are non-removable. Let's see here. Okay, for this one, saying that the bottom cannot be 0, it's a little more tricky than just saying like t squared minus 9 cannot be 0. So the idea is, if I factor it out, t plus 3, t minus 3, they all have to be numbers that are greater than 0 because, oh wait, no, that's not true. I was thinking that there was a square root on there. All right, back up. Let me just make more sense. Okay. These also have vertical asymptotes. Yeah, so it is as simple as just saying the bottom cannot be 0, which means that when, t is -3 and t is +3, all right, these are also vertical asymptotes, and those are both non-removable. Except that, okay, here's what I was missing. Except that right here, you can always take square roots of positive numbers, so actually any negative numbers are outside of the domain. So I mean, it is true that t cannot be -3, but it's not because it's a vertical asymptote, okay? It's because t can only be greater than or equal to 0 because you can only square root positive numbers. So t can only be greater than or equal to 0 with the exception of it cannot equal 3. And then at 3, it's non-removable. And like, I guess all those are non-removable too. All right. And then this last one, if I factor this, here we go. This one, okay, has a hole at 2 and a vertical asymptote at 3. And what we have to do is see if the hole gets filled in by this other point. Well, when I plug in 2 to this, once I reduce it, I get 1 over 5. Now this is plugging in the hole at 0. So there's a hole that exists at the point 2 comma 1 over 5. So it like comes up here to like 1/5. There's a hole, and then there's a point down there, you know? Okay, so it is not filled in. So these are both discontinuities. That one's removable, and that one's non-removable. The way that we remove it is we would just say, oh, let's fill it in at 1/5, and then we would remove it. Okay, so that's what, little bit of review on what that stuff means. Cool, fun. Oh, look, that's funny. This is that question that I just did. Man, sometimes I should like really look ahead because I just, anticipate some really good information here. Okay, that crosses out. There's a hole at 2, and when I fill the hole, right, it's at 1 over x plus 3. So it's at 1/5. So if this is 1/5, then the function is continuous at 2. Okay, fun times. Find a and b which make the function continuous. All right, now, what we have to do is we know that this is a line. Okay, 1/2 x plus b, that's a line. We know that's a parabola. Lines and parabolas are continuous. So the only thing we have to check is at the point where they meet up. When this one comes and this one comes, are they going to meet up together? Okay, so it's two different equations right here. -2. I'm going to plug in -2 right here. I get 1/2 times -2 plus b. So that's -1 plus b. And then I'm going to plug in -2 right here. And I get a times -2 squared. So that's 4a. So my first equation is 4a has to equal -1 plus b. Okay. Now I'm going to do another equation, this time seeing what happens at 1. Where will they meet up, okay? So if I plug in 1 right there, I get 1/2 times 1 plus b. And if I plug in 1 right there, I get, that's 1/2 plus b. And then I get a times 1 squared, which is a. So my next equation is a equals 1/2 plus b. Now I have a system of equations that I can solve, okay? We have to make one of them negative for the b's to cancel out. The easiest way to do that, let me just make this negative. The b's cancel out, okay? So a minus 4a, I get -3a equals 1 plus 1/2. So 2/2 plus 1/2 is 3 over 2. And when you divide that, I mean, you can do that on your calculator, or if I divide both sides by -3, the 3's cancel out, and I get a is -1/2. Okay? And then, let's say I plug it into here to get b. -1/2 is 1/2 plus b. If I subtract the 1/2 over, b is -1. Okay, so a little system of equations to see where those things are going to be continuous. All right, for 21 now, it needs to be continuous and differentiable. Brother, all right, let's do it. Continuous means that when we plug in 1 here for x and 1 here, they have to be equal, all right? Let me move this down there. All right, so if I plug in 1, now remember I'm plugging it in for x, a times 1 to the third, so a minus b plus 7. And when I plug in 1 to the bottom, I get, I plug in 1 there and there, -b plus 3b. okay? Just because I'm like seeing this right off the bat, this equation is a little bit simpler if I get that b over there. So a plus 7 is 3b. Okay, so that's one of my equations. Now, in order to make this differentiable, I have to perform the same like operation on the derivative though. Now, let's take the derivative. Let's start with that one. 3 comes down in front. 3ax squared minus b, and that goes away. Let's take the derivative of that one. 2 comes down in front. Negative 2bx. And 3b is a constant, so plus 3b. This is less than or equal to 1. This is greater than 1. Okay, now I do the same thing. I take 1. I plug it in here. I get 3a minus b. I take 1. I plug it in here. I get negative 2b plus 3b. Okay, negative 2b plus 3b is b. And if I add that over, I get 3a is 2b. Okay. Dude, I could do substitution or elimination here. I think I'm going to go ahead and do substitution. It's like slightly easier. And I'm going to solve this one for a. And then plug it into here. So 3a, which is 3b minus 7, equals 2b. Distribute that. 9b minus 21 is 2b. Subtract the 9b over, just like algebraing the absolute crap out of this problem. So then that gives me negative 7b, and b is 3. And I can really go back up to any of my equations, but that's honestly probably the easiest one. Low power. Okay, a is 3 times 3 minus 7. So 9 minus 7, a is 2. So if a is 2 and b is 3, this will be continuous and differentiable. All right, amazing. Let's get these next couple of questions out of here. I think I'm going to have to write them down here. 22 is y is 3 over x. Now, guys, just for ease of taking derivatives, I'm going to write that as 3x to the negative 1. And then 2 square root x. I'm going to write that as 2x to the 1/2. And it wants me to find the second derivative. Okay, here we go. First derivative. Bring that down. Negative 3x to the negative 2. Bring that down. 1x to the negative 1/2. Second derivative. Okay, bring that down. Positive 6x to the negative 3. Bring that down. Positive 1/2 x to the negative 3/2. That's a perfectly fine way to write it, or you can write it like this. Okay, also a perfectly good way to write it. We haven't done derivatives in so long. That was kind of refreshing. Okay, find dy dx. All right, this one is 3x squared minus 2y squared equals 4xy plus 20. Okay, you guys, this is an implicit question. We haven't done that in a minute, right? That's why these reviews are so good, because they're really going to help you stay on top of everything for the AP test, right? Okay, 6x minus 4y dy dx equals product rule. I'm going to put the 4 with the x, so derivative first times the second. First derivative of the second, and gone. Okay, I want to get the dy dx's on the same side, so I'm going to bring this over to here, okay? So I'm going to leave the 4x dy dx, and when I bring this over, it's going to become positive 4y dy dx. And then on this side, okay, I'm going to leave the 6x, and I'm going to bring over the 4y. So anything with a dy dx on one side, anything without on the other side. Factor out a dy dx. And then solve it. So dy dx is 6x minus 4y over 4x plus 4y. Do not try to cross anything out unless you can do it from all four parts. Well, first of all, don't simplify if it's an FRQ, but if you could take it out of all four parts, you could simplify. So for example, this, everything divides by 2. Okay, and so I get that. All right, 3x minus 2y over 2x minus 2y. Okay, 24 says find the points. Now it underlined that. Why did it underline that? Because I need to do a coordinate point. Which the graph from problem 23 has vertical tangents. Okay, guys, horizontal tangents is where it equals 0. Vertical is where it's undefined. So what I would do is, yeah, horizontal tangents would be the top is 0. Vertical tangents would be where the bottom is 0. So if I set that equal to 0, divide by 2, it's basically all the points on the curve where x equals y. How am I going to find the points on the curve where x equals y? Well, the equation of this was, this is up here, right there. Okay, 3x squared minus 2y squared. Let me just write it down real quick. And then it was equals 4xy plus 20. Okay, let's find all the points on this curve where x equals y. That's a little trippy, but basically, you guys, if x equals y, let's take all the y and let's replace by x. So to say 3x squared minus 2x squared equals 4x times x plus 20. You could have also done this with y and replaced all the x's with y's. All right, 3x squared minus 2x squared is x squared equals 4x squared plus 20. If I subtract that over, negative 3x squared is 20. This is getting a little weird. This is like not working. X squared equals 20 over negative 3. Hold on a minute. I have a mistake in here. Okay, just found it. How many of you found my mistake before I did? Raise your hand. All right, just kidding. Here's my mistake. Look. When geez, this is why we don't simplify things. Look at what I did when I simplified. I changed that plus into a minus, and I did not catch it. Okay, that's going to change some things. I was like, this is going to have no answers. That doesn't make any sense. All right, that changes some things. That means that x equals negative y, which is a little bit different, or y equals negative x. Like you can use either of those, okay? So what would that change over here? Well, y is negative x. So if I plug in a negative right here, guess what? That changes nothing. But over here, y is negative x. That does change it. So the left side is not going to change, but the right side, 4x times negative x is negative. And then I could solve it, okay? Because when I add it over, I get 5x squared equals 20, x squared equals 4, x is the square root of 4, which is plus or minus 2. Now, if x is plus or minus 2, what does y equal? Well, let's figure this out. X is 2 something, negative 2 something. If I plug into the equation y equals negative x, if I plug in 2, I get negative 2. If I plug in negative 2, I get positive 2. Okay, so it's at those points, 2, negative 2, and negative 2, 2, where this thing has vertical tangent lines, all right? This is an interesting enough question that we don't usually get to see very often. Plug this in before I die. Not before I die, of course, but before it dies. These just always make cool things. Okay, 4xy plus 20. That's nuts. All right. And so basically I can see the point 2, negative 2. I'll go ahead and label that one. And then the point negative 2, 2. And I'll label that one. And can you guys kind of see right along those points that there'd be a vertical tangent line there? Okay. So awesome. That's good. That's good. All right. That was 24. And then 25. Find an equation of a tangent line to graph of problem 23 at the point negative square root of 20 over 3, comma 0. Okay, so now we're looking at a new point. The new point is, and this is not a calculator question, but just sometimes I like showing you guys things. Okay, comma 0. All right, so that's that. And it wants the equation of a tangent line there. Okay, in equation of a tangent line, we go y minus y1 equals mx minus x1. All right, y minus, the y value was 0, and the x value was square root of 20 over 3. Okay, now my derivative, when I found that, was 3x minus 2y over 2x plus 2y. Okay, and I'm going to plug in the point. That's a 3. The point square root 20 over 3, comma 0. Okay, let's see what we got. 3x minus 2y, 2x plus 2y. I'm just making sure I'm doing this properly. All right, so let's figure this out. If I plugged it in, oh, and it was negative. See, I keep catching these little mistakes. My goodness. 3 times negative root 20 over 3 minus 0, and then 2 times negative root 20 over 3 minus 0. Okay, well, we don't need the minus zeros, and then those can cancel out, and so I just get 3 over 2. There's the equation of the tangent line. So let's check this out with the equation of the tangent line here, and we're going to look at how freaking awesome we are. Okay, y minus y1 equals m parenthesis x minus x1, which is negative square root 20 over 3. Look at that equation of a tangent line. All right, and now you guys can feel awesome that you did this entire review. It was a great review of everything, including chapter 8. All right, see you guys.